We know that tabular Q-learning and linear equations work well for simple, constrained environments. But force those methods to process massive, high-dimensional state spaces, and the mathematics completely fracture under the weight of the data. An environment like an Atari game outputs raw pixel frames, often an 84 by 84 grid per screen. The number of possible state combinations in that continuous visual space approaches infinity, making manual feature engineering mathematically impossible. Deep learning solves this. By deploying convolutional neural networks, the system takes in raw, high-dimensional data and automatically extracts the necessary spatial features on its own. When engineers bolt that deep neural network directly onto the Q-learning algorithm, they create the Deep Q network, or DQN. This solves the state space problem. But introducing a highly nonlinear network directly into reinforcement learning destroys the theoretical convergence guarantees that tabular methods rely on. To understand how modern control systems function, we have to map the engineering evolution from this unstable DQN architecture through DeepMind's stabilization interventions all the way to advanced actor-critic systems. Scaling reinforcement learning to complex real-world environments requires engineers to intentionally abandon mathematical safety and learn to control architectural instability. Standard DQN is built for architectural efficiency. Instead of taking both a state and an action as separate inputs, the singular input layer takes in only the raw environmental state, like an 84 by 84 stack of pixel frames. The hidden convolutional layers then scan those pixels, compressing the raw visual noise into abstract spatial features the algorithm can actually calculate. The network then branches out to the output layer, calculating and outputting a discrete numerical Q value for every possible action available in that specific environment, all at the exact same time. Because the Q-learning update rule requires taking the mathematical argmax across these discrete outputs, standard DQN can only execute discrete commands, like pushing a directional joystick. It cannot output smooth, continuous control actions, like the angle of a steering wheel. The second major limitation is severe internal instability. The DQN architecture combines three specific reinforcement learning techniques that break down when layered together. The first component is function approximation, introduced by the highly nonlinear deep neural network itself. The second is bootstrapping, where the agent updates its value estimates based on temporal difference estimates. The third is off-policy learning, where the algorithm learns the optimal target policy while following a completely different exploratory behavior policy. Tabular Q-learning guarantees convergence because it relies on linear operations. Combine these three nonlinear and off-policy elements together into what engineers call the deadly triad, and the system is mathematically guaranteed to oscillate wildly and diverge. Deep Q networks are broken by design. They require massive external engineering interventions just to keep the training math from exploding. The first intervention addresses data correlation. Deep learning networks require training data to be independent and identically distributed. But an agent playing a game sequentially generates highly correlated frames. Training on that correlated stream causes catastrophic interference. The network violently overfits to its immediate local situation and entirely forgets past lessons. The solution is the experience replay buffer. The agent stores all past transitions, the state, action, reward, and next state, in a massive external database. During training, the system pauses and pulls a random mini-batch of these past experiences. This breaks the temporal correlation of the frames and drastically improves sample efficiency by letting the network learn from rare, high-value transitions multiple times. Randomizing the training batch does not randomize the agent's behavior. An epsilon-Oglidi behavior policy is still strictly required during the simulation to explore the environment and feed diverse data into the buffer. The second major intervention targets the standard Q-learning target update equation, specifically the regression target, y. The value of y depends directly on the active network weights. Every time the network updates its weights to move closer to the target y, the target itself shifts. The algorithm simply chases a moving target. To solve this, engineers created target networks. They clone the active network to create a secondary target network, whose weights are completely frozen in place. By holding those target weights still for thousands of steps, the regression target remains artificially stationary. This provides a stable, fixed point for the active network to gradient descend toward. Buffering memory and delaying weight updates do not solve the mathematics of the deadly triad. They simply pause the instability long enough to trick the network into achieving local convergence. Even with these stability patches, value-based methods like DQN always eventually converge to a deterministic policy, selecting the single highest value action. In environments that require unpredictable, stochastic strategies, determinism ensures failure. Policy gradient methods take a completely different path. Instead of estimating state values, they parameterize the policy itself directly as a mathematical function. Instead of Q-values, the network takes the state and directly outputs probability distributions for each available action. This solves the continuous action problem natively. The network outputs the mean and standard deviation of a continuous probability density function, allowing the agent to continuously sample smooth, fluid control signals. The algorithm directly adjusts the policy weights to perform gradient ascent on the performance surface, constantly climbing toward the maximum expected return. Because it relies on direct gradient ascent, the system is highly exposed to non-convex optimization problems. If it climbs a small local hill, it can get permanently trapped in a local optimum instead of finding the global maximum. To execute this, we use the policy gradient theorem, which relies on a mathematical identity called the log derivative trick. It allows us to calculate the gradient of our performance objective without knowing the environment's underlying dynamics, by rewriting it as an expectation of the policy's log probability multiplied by a value metric. The Monte Carlo policy gradient algorithm, known as reinforce, plugs in the fully sampled episodic return, GT, as that value multiplier. This chart tracks the catastrophic variance that reinforce generates. Because GT accumulates the entire episode, making a single terrible move at the very end of a 10,000-step game plummets the total return into negative territory. The algorithm then blindly decreases the probability of all of 9,999 brilliant moves that preceded it. Actor-critic architectures were engineered to solve this specific variance problem. Instead of waiting for the full episodic return, the architecture introduces a separate critic network to estimate the value function. The actor then updates its policy using the critic's immediate, bootstrapped one-step temporal difference target. This hybrid architecture bridges the two methods. It utilizes direct policy optimization for fluid, continuous control, while deploying a value-based critic to effectively filter out the mathematical noise of the future. Up to this point, all these algorithms have utilized discounting to artificially shrink future rewards, ensuring the sum of an episode remains mathematically finite. While discounting is a vital tool for ensuring convergence in episodic games, it creates a problematic time bias in continuing tasks. For an industrial robotic arm operating indefinitely, we shouldn't prioritize the next 10 seconds over the next 10 hours simply because of an arbitrary discount factor. For these infinite horizon environments, engineers discard discounting and implement the average reward formulation. Instead of a discounted sum, the metric evaluates the true long-term expected reward per time step, measured as the number of steps approaches infinity. This shifts the entire objective metric from an absolute state value to the differential value function. Differential value measures how much better or worse a specific state is compared to the global environment average. Because it relies on a universal average, the entire calculation functions perfectly without ever requiring a designated starting state. These two equations display the mathematical elegance of the architecture. Transitioning to continuous operation requires zero structural changes. As proven by Sutton's team, the exact derivative of the expected return holds identically across both the discounted and average reward formulations, extracting raw pixels through convolutional networks, pausing internal divergence with memory buffers, replacing variance with bootstrapped critic estimations. Mastering deep reinforcement learning requires understanding strict mathematical trade-offs between value estimation and policy gradients to architect the exact mathematical structure your environment demands.